All right, this is our last installment of Chapter 7 to kind of get it underway, get us back in place, I should say. We were talking about quantum numbers, and let's just imagine we have something that has an n equals 5. What that tells us is there's a possibility of there being an L equals 0, an L equals 1, an L equals 2, an L equals 3, and an L equals 4 orbital. And once we know that that means there's a whole bunch of possible orbitals in something called the n equals 5 shell. So to make up n equals 5, you got to have all these guys, all these possible orbitals. And we also know that if there's an L equals 0, the rule says that there's going to be a certain number of orbitals, m sub L. So if it's L equals 0, then we're going to range from minus L to positive L. And since 0 is neither negative or positive, we only have one possibility, that is m sub L equal to 0. And in there we can put two electrons, a plus 1/2 and a minus 1/2. So that's our possibility, two electrons in this m sub L equals 0 orbital, this L equals 0 type of shape of orbital. By the way, what does that 0 mean? Does it mean there's no orbitals? Actually, it just means there's one quantum number, so there's only one orbital. So there's one quantum number, so there's one orbital. That'll make more sense when we do the next example. L equals 1. M sub L can be minus 1, 0, and plus 1. So there are 3 orbitals. 3 orbitals, into which we can put 2 electrons. We can put up and down, up and down, up and down. That looks like a possibility of 6 electrons, doesn't it? So for this guy right here, this L equals 1 and this L equals 0, we can see that there are possibly 2 electrons in the L equals 0, 6 electrons in the L equals 1. Let's go back to our periodic table and take a look. Ooh, scrolling back up, and here we are in our periodic table. If we take a good close look at this, if we take a good close look and erase everything here, if we remember correctly, this is the P, this is the S, and this would be the D. In the D, this and the S orbitals, there is room for 2 electrons. So in other words, if L is equal to 0, that's another way of saying S orbital. And here's a way, if we look over here, if L equals 1, it has 1, 2, 3, 4, 5, 6 places for electrons. Therefore, we would call this a p orbital. So L equals 1 and p orbitals are the same exact thing. No difference at all. So a p orbital, L equals 1, they tell us the same piece of information, that is the shape of the orbital. Great. Let's go back and do one more. One more. L equals 2. We'll look at that one. We can go from minus 2, minus 1, 0, plus 2, and plus 1. Doesn't matter what order we do this. And if we look at it, there's 5 orbitals. Therefore, we can have 10 electrons. If I go back up on my periodic table and I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there are 10 electrons in the d block. So if L equals 2, that's the same thing as saying we've got a d orbital electron. How many d orbitals are there? Well, there's going to be 1, 2, 3, 4, 5. We need 5 d orbitals to house 10 electrons. How many p orbitals? We have 6 electrons. We have to have 3. 1, 2, 3. And there's 1 s orbital in any one of these rows. So we've just kind of showed ourselves how the energy level diagrams are now going to split even further. We saw the split here once, all right? And then we saw it split even further here for the p orbitals. Now we have information which says it's got to split even further. So let's go take a look at that. Here is what an energy level diagram looks for a very complex atom. This is for chromium. Chromium. If we look carefully, this is what the hydrogen atom looked like. It had n equals 1, 2, 3, and 4. With chromium, though, with multiple electrons, we end up having a 1s, a 2s. That means n equals 1, L equals 0. That would be a 1s. This is a 2s. That's an L equals 0 again with an n equals 2. All right. And as you keep going through this, you can see, take a look at this, press pause and check it out, but this all fits, and we've just put in 24 electrons for chromium, and that's it.